fun?
Yes. I don't know if it's the first time I used it here. I think this whole class is being recorded on that one. Not positive. Anyways, chalk. Reminder of the big things we talked about last time. We talked about our rules of derivation. Our rules of derivation, we introduced 3 rules for derivation so far. Derivation was basically a proof. And so there's 3 rules that dictate what we are and are not allowed to do in our proofs, in our derivations. The first one we called rule P. We may introduce a premise at any point in our derivation. It can be line 57 of our derivation. We can introduce a premise, any premise we want. We just have to keep track of what lines depend on that premise, so we keep track of what it is we prove. Our next rule, the rule we use the most often, rule T, we can introduce some sentence or some statement S into our derivation, provided it is tautologically implied by previous lines.
We get
One previous line, 2 previous lines, 3 previous lines, take their conjunction. If they tautologically imply S, it's valid to introduce S into your derivation.
Can you explain to me what derivation means real quick?
It's our proof thing.
Oh.
It's when I'm writing out our proof, I say 1, we have as a premise this thing, and we're constructing some proof.
The whole thing's a derivation.
The whole thing's called a derivation.
Okay.
Okay. And then the last rule of our derivation, this was the weirdest one, and you guys gotta catch me. I kept calling this rule conditional probability. Why I was calling it conditional probability, I have no idea. This is the rule of conditional proof. Nothing to do with probabilities in this class. We're not talking about probabilities. I don't know why I kept saying that. It's just a normal thing to say after conditional proof, not conditional probabilities. Okay, so rule CP, the rule for conditional proofs. If we can derive S from R and a set of premises, then we may derive R implies S from the premises alone. So this was our rule that allowed us to conditionally introduce a premise that we later got rid of later in our derivation. And we'll redo some proofs that we did to remind us of our intuition for this. So we'll redo example 2 here. Now, I didn't want to move around the projector a lot, so I just wrote out what the premises were. So the premises were right here, and I'll read the sentences once I write them all out so that we can see them. So this was, our first premise was C implies D implies B. So we're starting our derivation. Well, this thing right here is called this derivation. This was a premise. This is the rule we're using, rule P. Not sure how much space I'll need. And it only depended upon premise 1. 1 referencing the line that the premise was introduced on. 2, another premise we had was not G or C. Was not G or C. That was a premise. And the only premise it depended upon was itself. And then 3 was a premise D. D, that was a premise. And it only depended upon itself. Okay, now I'll read the paragraph that we were actually talking about. Oh, and what we're trying to prove is G implies B. So maybe write that over here so that we remember what we're trying to prove. We're trying to prove G implies B. All right, so the actual sentence was, if the Cards are third, then if the Dodgers are second, the Braves will be fourth. So that was this premise. The second one was, either the Giants will not be first, or the Cards will be third. The next one was, in fact, the Dodgers are second. Therefore, if the Giants are first, then the Braves will be fourth. Okay, so that was the actual paragraph. That's what we're trying to prove. Here's our derivation just thus far. So we're trying to show that G implies B. I thought on the second one we didn't need to introduce a conditional premise, but maybe I'm remembering that wrong. I have a way of doing it without. No. So I guess that was only example 1. Probably should start with that. Oh well. Good to see all the rules in action in one go. Okay, so here's our premises. We're trying to show that this is the case. Now the first thing we're going to use is rule P. We may introduce a premise at any point in our derivation. The premise I'm going to introduce is G. And I'm going to indent it to remind me that later I'm going to try and get rid of this as a new premise. Because I want to show that just these three premises imply this is true. When it's all said and done, I don't want to have had to relied on that premise. All right, so we're introducing that. And this is where I'm starting my conditional proof, so I put a CP here to remind me I'm starting my conditional proof. It's a premise. And so it depends upon just itself for. So we introduced a new premise. Okay, line 5. If I know G, and I know that it's not G or C, from these two together I can conclude C. I know either G is false or C is true. I know that G is true, therefore C has to be true. Right? You see the logic there? That's a C. This says G is false or C is true. Either not G or C.
The whole statement is true. So, like, for instance, if G is true, then it would be, in this case, false. Or C is true.
It's given to us that this whole thing is true. So we know either G's false or C's true.
Oh. Okay.
It's a premise. Okay.
Yeah. Okay.
So we know not G or C. So we know G's false or C's true. And now we're saying G's true. Well, if G's true, and we know G's false or C's true, C must be true. Okay, so from this we can conclude C. This is tautologically implied by lines 2 and 4. Tautologically implied by 2 and 4. And so now we're using premises 2 and 4 so far in our derivation. This line of our derivation depended upon those two premises. Okay, so now we have C. If we have C, what do we have? Then we know D implies B. This says if C is true, then D implies B. This says C is true. Put those two together, and we get D implies B. So 6, we know that D implies B. D implies B. That is tautologically implied by 5 and 1. By 1 and 5. And so now, this is all dependent on premises 1, 2, and 4. This conclusion thus far is only the case if we know that line 1 is true, and line 2 is true, and line 4 is true. If we know those three premises are true, then we know this is true. That's what we're saying so far. This is true if those three premises are true. Good? All right, so now, if we know D implies B, oh, D is the premise here. Okay. So here, premise 3 says D is true. 6 says D implies B. We put those two together and we conclude B must be true. And this is tautologically implied by lines 3 and 6. And so now this is using premises 1, 2, 3, and 4. Right?
The premise being that all 1, 2, 3, and 4 are all true. Is that what that's what you mean?
What we're saying is that if premise 1, 2, 3, and 4 are true, then B is true.
Okay. Interesting.
That's what every line in our derivation is saying. This is saying we know that this line is true if premise 1 is true. In other words, this is true if this is true. So with the premises, it's obviously the case. As you get further down to more complex ones, we're saying C is true if we know that premise 2 and 4 are true. Make sense?
I see. Okay, so if something's true, then it's true. So you always would add the number, the step, or whatever you call it, to that set.
Always add the premise that it's assuming is true.
Which makes
to
that
set.
makes sense.
Yes.
Okay.
So you're always keeping track of this is implied by these four premises. That's what we're saying. Okay, so now we're going to use rule CP. We just really showed that these three premises and G implied B. Therefore, these three premises imply G implies B. So this is where we can get rid of our premise. So we're saying line 8 is now G implies B. This is using conditional proof. And then I put the line our proof started on to where it ended, from 4 to 7. From 4 to 7. And now the only premises that we're dependent upon are 1, 2, and 3. That's using this rule. This rule says if we can derive S from R, in our case S was was B. So in our case S was B, and R for us was G. So if we can derive B from G and a set of premises, then we may derive G implies B from the premises alone.
This is almost kind of like a way of simplifying a whole bunch of logic or something like that.
No. These are the three rules that we always have to follow in a derivation, in a proof. These are the only three rules we can use when we prove something. Our rules of logic are used in rule number 2. This is where we use all our rules of logic. Our rules of logic were all the little pieces we were using when I said, notice that, so pick any line right here, we concluded C. How did we do that? We concluded C from lines 2 and 4. We said, this implies this is a tautology. Or sorry, this and this implies this is a tautology. That was a rule of logic. A rule of logic that this and this implies this is a tautology. That's a rule of logic.
As a reminder of tautology, it's something to do with
something that is always true.
Yeah. Okay.
Here's a list of a bunch of the tautologies that we use over and over and over again.
And you're saying those are always true.
These are all always true. You do the truth table for any one of these, and you're going to get straight truths.
Fascinating.
And so these are the common rules of logic that we use over and over and over again in a derivation.
And these are the only ones.
No, they're just the common ones.
Oh, okay.
You could imagine constructing some massive truth table with a bunch of terms that turns out to be a tautology. You have just discovered a rule of logic. It's perfectly valid and you can use it.
So this could technically be a rule of logic. Those three premises implies G implies B. It would just be a really big truth table.
Yes.
Okay.
Yeah, so everything we prove, we can then put in a bag and say, okay, now we have that as a proof. Because this is just saving us from the fact, this is just saving us from having to do the truth table. Now that's only going to be the case to begin with. Eventually we're going to do derivations for things that you can't do truth tables for. That will happen when we start introducing like quantifiers.
Alright.
But for now, yes. Every derivation has a logically equivalent truth table. And we could use truth tables instead of derivations, but they're tedious.
Every derivation has logically implied truth table.
Has a logically equivalent truth table.
Logically equivalent, okay.
So what I'm showing here is that these things and just write it out. What does this whole thing show you? It says that if you were to take C implies D implies B and not G or C and D, you take all that, maybe do big parentheses around here, implies G implies B. If you were to do the truth table for that whole thing, you'd find out that this is a tautology.
So all derivations are tautologies.
Thus far.
Okay.
We'll start doing derivations that you can't do truth tables for.
Interesting.
But yeah, thus far, every derivation we do has a logically equivalent truth table that we could have used instead. Okay, so that was redoing example 2, showing you each of the rules. Any questions on that derivation before we go to the next one? Alright, let's just do another one then. Probably use the same numbers. And those will probably be the same. Alright, so our next example, we had A implies B or C as a premise. A implies B or C. Remember, this takes precedence. So the parentheses would go like that if you're not used to the precedence yet. This is a premise, and it only depends on itself. Okay, our next one was B implies not A. B implies not A. That was a premise, only depends on itself. Our next one was D implies not C. D implies not C. That was a premise, only depend upon itself. And then we're trying to show A implies not D. Let me write that over here. A implies not D. That's what we're after. And to give you the words associated with it, since we don't have it on the projector, example 3, it says, if A wins, then either B or C will place. If B places, then A will not win. If D places, then C will not win. Therefore, if A wins, D will not place. Okay, so going to do similar to what we did last time. We're going to introduce A as a conditional premise that we ultimately get rid of. So my notation is to indent that. We're starting our conditional proof, and it only depends upon itself. Okay, so now if we know A, what do we know?
Then B or C.
Then we know B or C, perfect. So then we know B or C. This is tautologically implied by 1 and 4. And so now we are using premises 1 and 4. Oops. Okay? So we know B or C. What else can we conclude?
Not B.
We can conclude not B from this one. If we know B implies not A, we know if B is true, A is false, but A is true. Therefore, B has to be false. So we know not B. This one's tautologically implied by, which ones did we use? 2 and 4? 2 and 4, and now we're using premises 2 and 4 in this line. Okay, now combine those two together. We know B or C is true, but we know B is false, therefore
C is true.
C has to be true. That's tautologically implied by 5 and 6. And this is using premises 1, 2, and 4 now. Okay, so now we know that C is true. Now what can we conclude? We know if D is true, C is false.
It has to be not D.
And we know that C is true. So D has to be false. Exactly. So not D. This is tautologically implied by 7 and 3. Tautologically implied by 3 and 7. And now this is using 1, 2, 3, 4 for its premises. Now what did we just really show? We showed A implies not D with these premises. And so that ends our conditional part of our proof. So then we get A implies not D. That's using our rule CP, starting from 4 to 8. From 4 to 8. And now we're only using premises 1, 2, 3.
Could you define premise again?
A premise?
Yeah, like what's the difference between the, okay, so you have the conditional proof. Oh, interesting. But yeah, like is is a premise really just kind of like a statement, or?
A premise, yeah, it's just a statement we introduce into our proof. It's just that any other statement that depends upon a premise, we have to keep track of over here.
Why do we call it a premise?
Because we use this rule to introduce it. Every line we put in this proof has to be there because of one of these three rules. I can put this line here because of rule 1, P, so this is a premise. I can put this here because of rule 1, so it's a premise. I can put this here because of rule 1, it's a premise. I can put this here because of rule 1, it's a premise. Now, I personally indent it and remind myself that I'm starting my conditional proof with this premise. Maybe that throws you off. Maybe I should just keep a P here.
Wait, what? So, A is also a premise.
A is a premise, yes.
So what's...
But rule CP allows us to get rid of a premise. If I can derive S from R as a premise, and some other set of premises, then I may derive R implies S from the premises alone. So if I can derive not D from A and some set of premises, then I can derive A implies not D from the premises alone.
Okay.
So these four are using rule P. These ones are all using rule T. And then this one is using rule CP. And so every line in our derivation has to be justified by one of those rules.
This reminds me a lot of algebra.
You would use this to start your algebra. This is the foundations of algebra. That's the foundations of all math.
It just reminds me of, like, if you had an extremely complicated situation, you could solve it just using these rules. Like, to see what implies what. Something that maybe your brain couldn't even figure out.
Yeah, and that's hopefully the point with some of these. You get that big paragraph, and it's not obvious to you, is that argument valid? But you write it out, you symbolize it, you do the derivation, and you say, yes, that was a valid argument. Or maybe you find out, no, it's not a valid argument.
Yeah, it's like, does one value equal another value? And anyways.
All right, so, quick note now. We kind of already made this note. We've been using derivations. We could have technically used truth tables for everything we did so far. But the big disadvantage to using truth tables is that they're tedious. The disadvantage to using derivations, though, is that there's no, here's what you do next. If you're doing a derivation, you have no clue necessarily what the next step is you should take. That's why proofs are so hard to do as a general rule. There's no, here's the next step. When you're filling out a truth table, you always know the next thing that you should do. With a derivation, maybe I have you try to prove something, you could easily just get stuck and not be sure what to do next. Filling out a truth table, you always know what to do. So, a little bit of a trade-off there, but ultimately we're going to get to the point where we have to use derivations anyways. So, we're going to stick with derivations over truth tables. As general. We'll use truth tables where they're useful. Okay. Checking now if an argument is invalid. How can we determine if an argument is invalid? One way we can do that is we can check it with the truth table. We simply build out the whole truth table and check, is it a tautology? If it's a tautology, it's a valid argument. If it's not a tautology, it's an invalid argument. That's one straightforward way to do it. The other way we can do it is we can find an interpretation such that the antecedent is true, but the conclusion is false. If it's possible to do that, then the argument is invalid. Let's look at an example. I give you an argument here. I tell you the sun is shining, or the sky is blue. The sun is shining, therefore the sky is blue. It's an invalid argument. Although, notice that every single one of those sentences are true. So everything being true is not the same thing as a valid argument. Those are two different things. So let's see how we can actually test to say that this is an invalid argument. let's see, we'll use S for the sun is shining and B for the sky is blue. So premise 1 says the sun is shining or the sky is blue. Premise 2 is that the sun is shining. And we said therefore the sky is blue. Right?
Isn't the second one, the sun is shining, like, if the sun is shining, then the sky is blue? Isn't it like it implies?
No, it's just the sun is shining.
Okay.
I just made it up for a simple invalid argument that we could easily check with the truth table that didn't have a lot of pieces to it.
Interesting. All right.
So one way that we can see that this is invalid is we set the truth table for it. S, B. We'll do a column for the conjunction of our premises. So we have S or B and S. And then our whole argument is S or B and S implies B. This is our whole argument, right? And if the argument is valid, this should be a tautology. And we can quickly check. True, 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 false, false, true, false, false. Okay, this one, we have true or true and true is true. We have true or false is true. True and true is true. This one, we have false or true is true. And then true and false is false. So this one's false. And then if everything's false, it's false. Follow that? Okay, so now this one is just saying this implies this. True implies true is true. True implies false is false. False implies true is true. False implies false is true. Not a tautology.
Huh.
Therefore, not a valid argument.
How did you derive that? I don't know what you'd call these logical statements, or whatever, from your original.
This is saying this and this implies this. This and this implies this.
Okay, so when you draw that line underneath both of them.
That's shorthand for the therefore. Typically, you'll see arguments like this. 1, 2, vertical line, conclusion.
That's why I was confused.
Okay, yeah, sorry. All right, so that's one way we could have done it, kind of a tedious way to do it. Another way we could do it is to try and come up with an interpretation where the antecedent is true, so both our premises are true, but the conclusion is false. If we can come up with an interpretation where that's the case, then we're good. So I can say S, I'm going to interpret that to be 1 plus 1 equals 2. B, I'm going to interpret that to be 2 plus 2 equals 5. There's my interpretation. Notice S is true, B is false. Is it true that we have S or B?
Yes.
Is it true that we have S?
Yes.
Do we have B?
No.
Is B true? No. So we found a case where the antecedent was true, but the conclusion was false. If you can find a case, an interpretation that makes your antecedent true and your conclusion false, the argument is invalid.
And the truth table would always prove that.
The truth table always works. Yes.
That's cool.
This we call finding a counterexample. Find an example where the antecedent is true, but the conclusion is false. We call that a counterexample. And when your arguments get complex enough, doing the truth table is out the window. And so you have to come up with a counterexample. Make sense? All right. That ends that section. Next section was just on a bunch of useful tautologies. These are the tautologies that we're going to be using in the middle of derivations over and over again, where I say, and this line tautologically imply this line. We're basically going to be using these rules. So we need each of them to appeal to our intuition so that we feel comfortable just using them. So let's go over each of them and then write out a truth table if we need to make it quick. Whatever we got to do to make it quick. You got to feel comfortable with these because we're just going to use them all the time. All right, so the first one says, if you know P and you know P implies Q, then you know Q. Let's try a different way. We'll make P Donnie's wearing socks, Q Donnie's wearing shoes. If you know that when Donnie's wearing socks, Donnie's wearing shoes, and you know Donnie's wearing socks, you can conclude Donnie's wearing shoes. Good with this one?
Yep.
Cool. Next one. If you know P implies Q and you know not Q, then you know not P. Let's do that with the socks and shoes ones. You know that if Donnie's wearing socks, then Donnie's wearing shoes. And you know that Donnie is not wearing shoes.
That,
Hold on.
That doesn't,
Yeah, that's not right.
something, just because something implies, something doesn't mean you can make, it's logical, what's the word? It's the double arrow thing.
Whoa, my brain is missing something obvious right now. Because I said it backwards. If I'm wearing shoes, then I'm wearing socks. It's because I picked a bad example of a sentence. Alright, this is, if I'm wearing shoes, then I'm wearing socks. Okay, you know, if I'm wearing shoes, then I'm wearing socks. And you know I'm not wearing socks, then you know I'm not wearing shoes.
Oh, okay.
Okay, so I just picked bad sentences. So if you know P implies Q, and you know not Q, then you know not P. If you know if P is true, Q has to be true, but Q is not true, then P can't be true. Now, say a bunch of different ways till it clicks. That clicking with your intuition?
Yeah.
Alright, next one. This one we've used a couple times already. If you know P or Q is true, and you know P is false, then Q has to be true. You know P or Q is true, one of them has to be true, and you know P is false, then Q is the one that had to be true. If I know that you ordered the soup or the salad, and I know you didn't order the soup, then I know you ordered the salad. Okay, this one's super trivial. If you know P and Q are true, you know P's true. Okay, next one. By the way, I should probably say, the author with each of these rules, he puts the name next to it. All of these rules have names because, as I think a lot of it goes back to the monks in their monasteries were developing logic. They didn't have this nice syntax that we now have, although they were using the same chunk of logic. And so they would give names to each of these little chunks of logic so that they don't have to re-explain the whole thing. And so all of these have their different names. And I don't bother with most of their names.
Would you say these are somewhat the building blocks of all of these larger tautologies?
They are common building blocks. You could come up with your own building blocks.
But wouldn't those building blocks kind of be made of like more fundamental building blocks that essentially you can map out?
Quite possibly. All right, so next one. This one says, if you know P implies Q, and you know Q implies R, then you know P implies R. If every time P is true, Q is true, and every time Q is true, R is true, then every time P is true, R is true. And I'm sure that that one has a transitive name in it somewhere. All right, I know what this one's called. This one's called the law of absurdity. If P implies both Q and not Q, then P must be false. If P being true implies a contradiction, then P must be false.
So something that always will be false, then what it implies would always have to also be. Yeah, that makes sense.
Yeah, if a statement being true implies something impossible, then that statement can't be true. And so that statement has to be false. Okay. Or the way that it's more commonly said, if a statement being true implies an absurdity, then the statement must be false. And that's why it's called the law of absurdity. Okay. This one's similar to this one. If you know P is true, then you know P or Q is true. Because you know P is true.
Okay, yeah.
Yeah. Next one, simple one, law of double negation. This one's a bit trickier. Contrapositive, but this is one that's used left and right. One of the most common ones used. P implies, should have noted when we got to this line. These are all the common implications we use. Now we're going to get to the common equivalences that we use. Still tautologies. And the first one we did is P is logically equivalent to not P. That was an implication, that is, this is the same as this, and this is the same as this. This is saying something different up here. This is definitely not the same as this. Okay, so our next one is P implies Q says the exact same thing as not Q implies not P. Let's say that with words. If there's fire, then there's oxygen is the same thing as if there's not oxygen, then there's not fire. That make sense? Contrapositive, very common one. Let me know if you guys want to see truth tables for any of these, because we can do it. It's not jumping to your intuition. Next one, this is how we distribute a not over an or. Not P or Q is the same thing as not P and not Q. If you don't own a car or a house, you don't own a car and you don't own a house. Next one. This is how you distribute a not over an and. Not P and Q is the same thing as not P or not Q. If I say I own a car and a house, and you say that's not true, you're saying either I don't own a car or I don't own a house. If I don't own a car and a house, then either I don't own a car or I don't own a house. Good? Next one's just the commutative law. P and Q is the same thing as Q and P. Doesn't matter what order you say those in, you're saying the same thing. P or Q is the same thing as Q or P. Doesn't matter what order you do that in. Associativity. P or Q or R is the same thing as P or Q or R. Doesn't matter if you or those two together first and then or with this, versus or those two together first and then or with this. Similarly with and is associative, is the other way we say that. Good?
Yeah, that makes sense.
Okay. Next one, here's a really weird one. P or Q is logically, P implies Q is logically equivalent to not P or Q. If I say, if I'm wearing shoes, then I'm wearing socks, I'm saying either I'm not wearing shoes or I am wearing socks. If I'm wearing shoes, then I'm wearing socks says the same thing as I'm not wearing shoes or I am wearing socks. Good with that one? That one's kind of a weird one.
Powerful, because I can see a lot of cases where that'd be very useful.
Yeah, sometimes it's very useful to, instead of thinking about an implies, think about a or.
Not and Q, or not and
Not P or
and
Q.
Something.
Yeah, think about it in terms of ors. And if that appeals to your intuition, by the way, then you can see how vacuously true works as well.
Oh.
If you're perfectly comfortable with the notion that P implies Q is the same thing as not P or Q, then notice that this is true every time P is false.
What? That's true.
I won't lie to you.
I'd have to think about that.
So, with the implies, it's always just about finding some way to make it appeal to your intuition.
That's the best explanation I've seen.
Hey, if that works for you, that works for you.
Cool.
There you go. We got vacuously true. Okay, the next one is not P implies Q, means P and not Q. Let's make this one make sense. So let's say what P implies Q is. We'll say that if Donnie's wearing shoes, then Donnie's wearing socks. Okay, that's P implies Q. Let's say that statement's false. So I say, if I'm wearing shoes, then I'm wearing socks. You say that's not true. What are you saying? You're saying I'm wearing shoes without socks. You're saying you're wearing shoes and you're not wearing socks. If it's not the case that every time I wear shoes I wear socks, that means sometimes I wear shoes and not socks.
And okay, yeah. I mean, it makes sense. I just, like I said, I still get time to think about that.
No, it's fine. Each of these, you gotta stare at it until it feels obvious, and then it just feels obvious.
Yeah, I want us to go home and study all this. This is awesome.
Well, you'll get comfortable with most of this because we'll be using it over and over and over again. And we've already been using a lot of it.
Yeah, I want to get really familiar with the bill.
Okay? The next one, this is a piece of logic that we use to help us justify rule CP. This says if P and Q together imply R, then P implies Q implies R. If you know that when P and Q are true, then R is true, then you know that if P is true, then if Q is true, R is also true. This says if P and Q are true, then R is true. This says if P is true, then if Q is also true, R is true. And I think we actually did the truth table for that one last time.
That makes sense. Yeah, that makes a lot of sense.
Okay? And then these ones aren't equivalences, but these are basic rules of logic all the way back from Aristotle. It's always the case that you have P or not P. That's called the law of excluded middle. Either P's true or P's not true. And then this one's called the law of contradiction. It is not the case that you have P and not P. So P and not P is always false, so not P and not P is always true. Make sense? Any of those feel weird? Surprised we didn't write out truth tables for any of them.
No, they all make sense. What I would love to see though is this P implies Q is logically equivalent to not P and Q.
You're saying this one?
It's like one more.
This one?
I would really love to see that in a truth table.
We're doing P implies Q, and then we're doing, then over here, we're doing not P or Q. Okay? We have true, 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 false, false, true, false, false. And remember what we're saying is these two are logically equivalent. So true implies true is true. True implies false is false. False implies true is vacuously true, vacuously true. Right? Now, here, since they're both true, we have true. Here, since they're both, not P is false, and Q is false, so they're false. And for these two cases, not P is going to be true. So true and true.
It's just so weird. Don't understand.
Whatever makes it click. I don't know.
Huh.
Okay, you want to see any more of those, or should we move on? Move on? Well, since y'all yelled at once. And
What I love about this so
some
much
spectrum.
is that it breaking the term implies down to nots and ands.
Well, you can reduce every single logical operation to the NAND operation, which is not AND.
Yeah.
And the notation we use for that is this. An AND with a line through it. And I can use NAND to create a NOT, to create an AND, to create an OR, to create everything.
That is shocking.
And so you can just use that one logical operator and reconstruct all the propositional logic.
So we use the term implies just to simplify.
It's just a
More
convenient
complex.
one to use.
That is so weird.
So we don't need implies, we don't need any of them. We can just use NAND and go from there. And so in my computer architecture course, I had to build circuits. And we started by doing it exactly like that. We first built a NAND circuit. And then that's the only one that we built from scratch. And then with that one, we start putting those together to build an AND circuit or an OR circuit, because your basic computer needs to be able to do basic logic. So I had to build a bunch of little circuitry that could do basic logic. Started with just a NAND gate.
Do we have basically all of the most useful or used logical symbols, being that logically equivalent, implies, and, or, not, NAND, and then XOR? Those are the only ones you've shown so far.
Sure, technically there's 16 of them,
Oh boy. Okay.
because you can come up for one for every possible combination of how to fill out this. When you're talking about applying to only 2, I could also come up for operators that apply to 3 at a time.
Huh.
But if I do P and Q there, well, we're off the camera now. Put it over here. And now I do P, whatever symbol I want, Q, based off of what these are, true, 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 false, false, true, false, false. I have 2 options for what goes here, 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 for a total of 16 options. For each of those 16 options, I can come up with some symbol there and say, this is what you do in this case.
And we do have symbols for all those.
I don't know if we have symbols for all of them, but you can make them up if you want. And then you have them, and you can use them. It's just, you don't need them. And technically, you can just use the NAND operator.
So
But-
normally we'll just use a combination of other symbols to create those scenarios.
Yeah, we can create them as needed for those other scenarios. We use ones that kind of appeal to our logic.
Our sentence structures and whatnot.
Yeah, just what's intuitive, what's easy to use. Because NAND is one that is hard for you to just think about.
That is.
Whereas for a computer, it's just as hard to think about NAND as AND. There's no reason that one's easier than another. But for humans, NAND is much harder for us to reason about than AND. So, yeah, we just pick whichever ones are useful and go from there. Okay, consistent. All right, what does it mean for a set of premises to be consistent? First, some intuition. You got 2 kids, Jack and Jill. They got in a fight, they come to you. You're wondering what happened. You say, Jack, what happened? Jack says, Jill hit me first. Jill says, no, Jack hit me first. You instantly know one of them's lying. The premise, Jack hit Jill first and Jill hit Jack first, are inconsistent premises. They can't both be true. Now, what if Jack says, Jill hit me first, and Jill says, yeah, I hit him first? Now those are consistent premises. Maybe it's not the case. Maybe Jack really hit her first. But the premises are still consistent. Maybe not true, but consistent. So, a set of premises is consistent provided that they could altogether be true. Otherwise, they are said to be inconsistent. So, a set of inconsistent premises are a set of premises that can't altogether be true. Make sense? Alright. Now, why do we care? Well, notice that what our rules of logic say. Our rules of logic say, logic says that if the premises are true, then the conclusion is true. Our rules of logic don't say anything about if the premises are false. We don't try to reason about false premises. We don't try to reason about what if the sky's blue and the sky's not blue. Let's reason about that. What can we conclude? Those are inconsistent premises. We don't try to reason about that. So logic doesn't even try to reason about inconsistent premises. Waste of time, don't bother. It just says, if the premises are true, then here's the conclusion. If the premises can't be true, we just call them inconsistent, we say, that's it, we're done.
Don't just say false.
Well, no, remember, logic is saying, what can you conclude from these things? What can I conclude if I know the sky's blue and the sky's not blue? I can't even know that the sky's blue and the sky's not blue. What do you mean?
Okay.
So we can't even get off the ground. So we just say those premises are inconsistent. And that's all there is to it.
Well, one of your logical statements over here was, where was it? P implies Q not Q. Because those were logically inconsistent, or what would you say?
Inconsistent premises?
Yeah.
This was, if P implies an absurdity, then P can't be true.
Yeah, then we just say it's false. Yeah, it's not true. It's false. I mean, isn't that a logical conclusion? That from an absurdity?
Yeah.
Okay.
Yeah.
So logic does work with absurdities.
Logic works with absurdities. We don't try to start reasoning about a set of premises that are inconsistent. I can't do a derivation starting with inconsistent premises.
Okay.
Given some set of premises, I can possibly eliminate one using the law of absurdity.
Okay.
I can introduce one conditionally and show, no, it can't be the case. And we'll see how that works. We call it a proof by contradiction.
It's kind of like what you're explaining right now.
No, this is different.
What I'm saying is, in your language, you're using an absurdity, therefore this is not logical.
Over there, we're saying, so we're doing a derivation. And in our derivation, I'm wondering, is P true? Well, if it's true, then we get some absurdity. Therefore, P has to be false. And we continue on our merry way.
Okay. Alright, yeah.
Okay. So, if our premises are inconsistent, we can't even get off the ground. So it's useful for us to know if our premises are inconsistent. So we have a test for that. No. Going back, maybe you remember criterion 1 and criterion 2. The two rules are two criteria that our rules of logic have to follow. All these rules that we developed here had to follow these two criteria. Otherwise, we couldn't call it a rule of logic. So criteria 1 says that we can only conclude true conclusions from true premises. So then, if we can derive a false conclusion, our premises can't altogether be true. And we must have inconsistent premises. So take your premises, and if you use valid rules of logic to come to a false conclusion, then you know that your premises are inconsistent. So it's one of the ways that you test that your premises are inconsistent. Can you derive something false from them? So showing our premises are inconsistent, two ways we can do it. One way is a truth table, and we can just look at the conjunction of all the premises, and if the conjunction of all our premises are always false, 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 then we know our premises are inconsistent. For example, P and not P. If we do a truth table for that, here's P. If we just have two premises and our premises are P and not P, P can be true or false. In either case, false, false. This is always false, therefore these premises would be inconsistent. So one is the truth table test.
Oh, so this is almost the exact opposite of a tautology.
A contradiction is the exact opposite of a tautology.
Okay.
I hate to say that language, but good intuition. I don't like saying the exact opposite. Either way. So one way that we can show that set of premises are inconsistent is take their conjunction. So if our premise is P and not P, take their conjunction, we always get false. Therefore, those premises are inconsistent. Another way we can do it is we derive a contradiction. If my premises allow us to conclude some contradiction, something that's false, then our premises can't altogether be true. And so they're inconsistent.
Say that again.
From criterion 1. Criterion 1 says that we can only derive true conclusions from true premises. So criterion 1 says if your premises are true, then your conclusion is true. Okay? Now let's say I came to a false conclusion. Then one of my premises had to be false. Because if they were true, my conclusion has to be true. So if you come to a false conclusion, one of your premises must have been wrong. So that's another way that you can show a set of premises are inconsistent. So we'll show both of them. Really quick, we'll do a small example and then we'll do a more complex example. First one. I give you as a premise, if I'm wearing shoes and I'm wearing socks. That's my first premise. Written out right here. Alpha implies beta. Alpha is I'm wearing shoes. Beta is I'm wearing socks. I give it as my second premise. I'm wearing shoes and I'm not wearing socks. That's alpha and not beta. So here's my two premises. Here's all the possible cases. We can have true, false, true, true. And this one, we can have true and false is false. True and true is true. False and true is, or false and false is false. False and true is false. Okay, so there's that premise. And now the conjunction of my two premises are true and false is false. False and true is false. True and false is false. True and false is false. The conjunction of my premises is always false. Therefore, these premises are inconsistent. Something's got to give if we're going to reason about this stuff. We can't reason about both of them together. All right, let's do a more complex example. This, probably get the projector up and going so that you can read the problem. Well, that's not very promising.
The sound it's making?
The fact that's not on.
I just fell asleep.
Did I close it? Oh, it was already open. Close on. Okay. Make that a little bigger. Will I be able to fit it? Yes. It really fits. Okay, looking for example 4. We want to see that. We just want to be able to read the sentence. Okay. Maybe move my camera. I don't know if my camera will be able to see sentence. And my work. Okay. Wait just a second. Okay, so we're doing example 4. And we're wondering, are these premises consistent? So the first premise is, if the contract is valid, then Horatio is liable. So it being valid implies he's liable. That's a premise, only depends on itself. Next one is, if he's liable, he will go to the bank. Or he will go bankrupt. So liability implies bankruptcy. Next one is, if the bank will loan him money, so M for loaning money, if the bank will loan him money, he will not go bankrupt. And then the last premise is, as a matter of fact, the contract is valid and the bank will loan him money. So the contract is valid and the bank will loan him money. The question is, are these premises consistent? And so we're going to find out. If we can conclude a contradiction, then the premises obviously are not valid. We'll need that just in case. Okay, so let's see. What can we conclude so far? Well, if I know B and M, if I know the contract's valid and the bank will loan him money, I for sure know the contract's valid, right? and this is tautologically equivalent, or tautologically implied by just line 4. And so this is still only dependent upon 4. Okay. If the contract's valid, then we know he's liable. So now I know he's liable. That's from 1 and 5. This is tautologically implied by 1 and 5. Now we're using premises 1 and 4. Okay. I know that if he's liable, he'll go bankrupt. So I know he's liable, and I know if he's liable, he'll go bankrupt. So put those two together, we know that he'll go bankrupt. That is tautologically implied by lines 2 and 6. And so now we're using premises 1, 2, and 4. Now, let's go back and look at this one. I know from 4 that the contract's valid and the bank will loan him money, so I know the bank will loan him money, that's M. And this was tautologically implied by just line 4. Okay? If the bank will loan him money, I know that he won't go bankrupt. So putting together 8 and 3, then I get not bankrupt. This was tautologically implied by 8 and 3. This is using premises 4 and 3, right? So, what do I get? I get B and not B. That's tautologically implied by 7 and 9. That's using all our premises 1, 2, 3, 4. And so, since all those premises together imply a contradiction, those premises are inconsistent. They're not altogether true. Something's got to give.
So that's when you know to stop, is when you have all premises.
I know that. Here's what I have here. I have something that's obviously false. And what did I derive it from? These 4 premises.
Which, of course, you have to have all 4 premises derived to.
Well, maybe I could just use 3 of the premises and get a contradiction. Then I know that only those 3 premises together are inconsistent.
I see. Okay.
Okay. So that's showing it's inconsistent. Now what about showing it's consistent? Maybe you want to show it's consistent before you get started on proof. So 2 ways that we can show a set of premises are consistent. Once again, we can do a truth table. And if when we write out the truth table for it, a T shows up anywhere in the conjunction of the premises, then they're consistent. It's possible for them to altogether be true. So that's one way you can do it. Another way you can do it is you can find an interpretation that makes all the premises true, but the conclusion and the conclusion true. If you can find some interpretation that makes all the premises true, not the conclusion, there is no conclusion, we're just talking about premises. Say again. To show that premises are consistent, you just need to come up with interpretations that makes the conjunction of all the premises true. That means it was possible for all the premises to be true. Okay, that's what I was trying to say. So now, go on to example 38. Let's see if I can move my camera so that we get more of the board without having to almost get it all. Just have to use the table. And maybe zoom in a little. Too much. See. Alright, we'll stop it. Should have played with that ahead of time and had a spot to put it. Okay. Get some space here. So next we were doing example on page 38. Here's evidence 38, some example here. And we want to know, are these premises consistent in this next example. So we'll just write it out up here. Here's what we're talking about, and we can kind of ignore their writing. All right, if war is near, then the army has mobilized. So our first premise, 1, is war is near implies the army has mobilized. Next one. If the army has mobilized, then labor costs are high. So army has mobilized implies labor costs are high. However, war is not near, and yet labor costs are high. So 3 is, it is not the case that war is near, and labor costs are high. So the question is, are those premises together consistent? So how can we test if they're consistent? We need to come up with an interpretation that makes all the premises true. So let's think of some interpretation we can make that makes them all true. If we could do something like W equals a sentence, 2 plus 2 equals 5. We can do A equals a sentence, 2 plus 2 equals 4. And we could do L equals a sentence, 1 plus 1 equals 2. So there's the interpretation I'm going to give to that. And let's check if all the premises are true. Is it true that if 2 plus 2 equals 5, 2 plus 2 equals 4? It's vacuously true. Kind of a weird one. Let's switch those so it doesn't mess with our intuition too much. 1, 1, 2, 2, 2, 4. Okay, let's try again. Is it true that if 2 plus 2 equals 5, then 2 plus 2 equals, or then 1 plus 1 equals 2? Sure. Okay. Is it true that if 1 plus 1 equals 2, 2 plus 2 equals 4? Yeah? Let's check our last one. Is 2 plus 2 equals 5 false? Yeah. And is 2 plus 2 equals 4 true? Yeah. So this interpretation made all these true. So the premises are consistent.
Okay.
Another way you can think about it is rather than coming up with sentences that are true or false, you can say, just imagine the case where if W is true, A is true, and if W is false, A is true, and L is true, then that's going to be true, that's going to be true, that's going to be true. False implies true is true. True implies true is true. Not false and true is true. So we found out an interpretation that assigned those exact same values. If you can come up with any interpretation, then the premises are consistent. So that's how we test for consistent premises. Notation that's useful to use from time to time is this fancy P. Same P we use for power set. I think we talked about that in computation theory, power sets. Power sets. Same P we use for power sets. In this context, it stands for the conjunction of all the premise. So this is shorthand for P1 and P2 and ... and Pn, assuming there were n premises. Just conjunction of all your premises. Useful shorthand. Alright, now we're going to introduce another rule. Rule RAA. So we have those 3 rules that we started with over there. Here's our 4th rule that we're introducing. This is the rule of reductio ad absurdum, or proof by contradiction for those of you who have had a math class before. It's a type of reductio ad absurdum. Reductio ad absurdum. Here's what the rule says. Can you see my finger on the camera?
Yeah.
Okay. Here's what the rule says. If a contradiction can be derived from your set of premises and not S, then S can be derived from your set of premises alone. So let's do a truth table for this and then say it again. So remember, this fancy P stands for the conjunction of all my premises. If we have 5 premises on there, this is P1, MP2, MP3, MP4, and P5 all joined together. right? S here is going to be some new statement that we're trying to prove, and C just stands for contradiction. So C is always false. It's just standing for contradiction. Now we can have 4 possible cases here. We can have the conjunction of all our premises are true, and S is true. We can have the conjunction of all our premises is true, and S is false. We can have the conjunction of all our premises is false, and S is true. We can have the conjunction of all our premises is false, and S is false. Those are all the possible cases. Alright. Not S over here. Don't think we really need that. That's false, true, false, true. So, all your premises and not S, that's these. So all your premises and not S, in this case, is false. In this case is true. In this case is false. In this case is false. Now, all your premises and not S imply a contradiction. False implies false is true. True implies false is false. False implies false is true. False implies false is true. Now over here, let's just do premises implies S. True implies true is true. True implies false is false. False implies true is true. False implies false is true. Notice that this and this are logically equivalent. So you have your set of premises. If S being false implies some impossible worldview, then S must be true, given that your premises are true. Make sense? All right, let's see an example using that rule now. And so, redo example 3 using proof by contradiction. Let's go back to example 3. Yell at me if you see it. Okay, and I guess it doesn't matter if we see the proof since we're doing it a different way. So we're going to do proof by contradiction. We're going to show that. Let's write out our premises as we go here. Let me erase that. Get started. So our first premise, we know that if A wins, then either B or C will place. So A implies B or C. Remember, the or has precedence. This is a premise, only depends upon itself. Okay, line 2. If B places, then A will not win. B implies not A. Premise only depends upon itself. 3. If D places, then C will not. And then, therefore, if A wins, D will not. So we're trying to show A implies not D. We get the same premises as him? Good. Okay. So, sorry. Premise 3. And just turn that to the same page, just in case. Okay. So I'm going to do a proof by contradiction now. I'm going to show that the negation of this is impossible, and therefore this has to be the case. So first I need to negate this thing that we're trying to prove. So this is A implies not D. What's the negation of that? Maybe you're not comfortable with it that way. Let's go back and use our rule over here. P implies Q is the same thing as not P or Q. So this implies this is the same thing as not this or this. So this right here is the same thing as not A or not this or this. You see that? And now I'm going to negate it. So now I'm going to negate this. How do you distribute a not over an or?
Flip the or to an and.
Flip the signs. Yep.
And nots.
That's right here. Not P or Q is the same thing as not P and not Q. So not this or this is the same thing as not this, which is just back to A, and not this, which is back to D. So A and D is a negation of A implies not D. As strange as that may seem.
That is very strange.
So 4. I'm going to introduce A and D as a premise, a conditional premise, but I'll just put P there so that you know what rule I'm using. Because I can introduce a premise at any point in my proof. Okay, so I introduce that as a premise. Okay, now 5. Now what do I get from that? Well, if I know A and D, I definitely know A, right? Tautologically implied by 4. There's some of my work over here now. Just remember that A and D was a negation of that. And so this is only dependent upon premise 4. Okay, 6. Well, if I know A, what do I know?
D.
We can do B or C if we want, or we can look at this one and we can do not B. I'm going to do that one first. So this and this tell me not B. I know if B is true, A is false, but A is true, so B has to be false. So I know not B. This is tautologically implied by 2 and 5. By 2 and 5, so now we're using premises 2 and 4. Okay. Now do what Mom just said. I also know from A that B or C is the case. So putting these two together, 1 and 5, I'm able to conclude B or C. So I know B or C, that's tautologically implied by 1 and 5. Okay, now putting these two together, I can conclude C is true. I know B or C has to be true, but B is false, so C has to be true. That's tautologically implied by 6 and 7. Oops, forgot to put premises over here. Sorry about that. 1 and 5, we're using premises 1 and 4. And now, 6 and 7, we're using all those premises, which are 1, 2, and 4. Nine, going all the way back to 4, I can conclude D. This was tautologically implied by 4. It's only using premise 4. And now that I know D, what do I know?
Not C.
Not C, from 3. So 10, I can conclude not C. This was tautologically implied by, what was that, 3? And 9. So we're using 3 and 4. And so now I can conclude C and not C. And that was tautologically implied by 8 and 10. And now we're using all these premises, so that's all of them, 1, 2, 3, and 4. Now we use rule reductio ad absurdum. And that was from lines 4 to 11. What does reductio ad absurdum tell us? It says that if your premises, together with the negation of some statement, imply a contradiction, then your premises imply just that statement. So I can conclude the negation of this statement. Here was S, here was not S. So my premises, together with not S, gave me a contradiction. Therefore, my premises alone, 1, 2, and 3, Give me the negation, give me just S, the negation of that, which is A implies not D. So then I can say A implies not D. That's using reductio ad absurdum from 4 to 11, and it enables us to get rid of 4 as a premise and just say 1, 2, and 3. So to be very clear, the fancy P here is shorthand, in this case, for the conjunction of just lines 1, 2, and 3. The S here is this statement. The not S is this statement. So we show that premise 1, 2, and 3, together with not S, this statement, imply a contradiction, C and not C. Therefore, we know that the premises by themselves imply S. We know that the premises 1, 2, and 3 imply S. This is derivable from just those 3 premises. And that's a reductio ad absurdum proof, or a proof by contradiction. Make sense? Kind of a weird one. We'll do one more of those, and then we can be done with new material for the day. I'll probably start with.
So we have so far we have 2 rules.
4 rules of derivation.
Derivation. Oh.
Tons of rules of logic. One of our rules of derivation, rule 2, says you can use your rules of logic.
Well, I'm talking about showing inconsistency, and if I understand correctly, if a contradiction can be derived from P and not S, then S can be derived from P alone.
Yes.
Now, is that a way to prove that there's a contradiction, or I never quite grasped the concept. Because like here we're saying, well, they're all F and they're all false, and then there's a contradiction, right? Yeah. But is there like other ways to prove that there's a contradiction?
Looking at it in our context over there, our initial premise were the 3 that the problem gave us. Those were just lines 1, 2, and 3.
Right.
Those premises were consistent.
Okay.
We could have proved it with some interpretation, but they were consistent. Introducing premise 4, which was the negation of what we were trying to do, now made them inconsistent, and we showed that. So the 4th thing that we tried to introduce suddenly made our premises inconsistent. So that 4th premise was a problem.
So why was it that you were able to just add that premise then? I never quite got that.
Rule 1, you can introduce a premise at any time. Doesn't matter what it is. You can introduce anything you want into your proof. That's a premise. Yes. You just have to keep track of which premises your conclusion relies upon. Because you're trying to prove something very specific in the problem. The problem said if, and it gave us 3 things to reason about, then it gave us a conclusion to prove. So I need to show, somewhere in my derivation, I need to have the conclusion we were trying to show, and over here in curly braces were just 1, 2, and 3, the 3 premises it gave me.
And so that worked. Because even though you
it worked.
You added a contradiction, or something inconsistent, I think, which was number 4, but you never ended up using number 4.
But I never ended up using it. I introduced it, and I wasn't sure. Does this make my premises inconsistent? And it turns out, yes, it did. Okay, so it can't be true. So its negation must be true. Maybe I'll try and be more explicit on this next one that we do. So number 4. Oh yeah, we had to go back for that one. They were referencing a previous section. Oh, way too far. Where is it? There's their proof. But where's the problem? Am I blind? Oh, this was redoing example 3. Okay. Oh, it's example 5, not 4. Okay, example 5. Maybe scroll their stuff off the screen so we can see it. And maybe that. This one's weird. Alright. So our first premise. If 25 divisions are enough, then the general will win the battle. So, if the divisions are enough, then we'll win the battle. Either 3 wings of tactical air support will be provided, or the general will not win. So either we get the air support, or we don't win. Also, it is not the case that 25 divisions are enough. Also, it is not the case that 25 divisions are enough and that the 3 wings of tactical air support will be provided. It is not the case that divisions will be enough and that air support will be provided. Therefore, 25 divisions are not enough. Therefore, not D. Let's see if we at least got the premises the same so we don't misunderstand anything. D implies W, A or not W, not D and A. Okay. Perfect. Okay, so we got to start the same way as him. Now, what he's saying in that paragraph is that these 3 things imply this. I can come up with this somewhere in my derivation where the only premises it depends upon are these 3. You might think I could do something like all I introduce as a premise, not D. That's a premise. And then say, done. I showed not D. No, because I showed not D from premise 4. I need to show not D from these 3 things. So you can introduce anything you want as a premise, but it doesn't mean you proved what you were asked to prove. So those are our 3 premises. Those 3 together are what we mean by this symbol. So these 3 are our fancy P in this case.
And we figured that out by the fact that
Reading the actual proof in the problem.
Yeah. Okay.
So far we're just codifying the problem. The proof says this, and ultimately we should be able to conclude that. Is our argument valid? Right? That's what we're testing for. Now we're going to do this proof by contradiction again. So I'm going to introduce D as a premise, get a contradiction, and therefore it's not D. So line 4 here, I'm going to introduce D, indent it. It's a conditional premise, something I promise I'm going to get rid of, just to help the reader. The author doesn't do that. It's just a habit I picked up from other people's proofs that I saw him do it. It was a good idea. So we introduce D now as a premise. Okay, so we have D. With D, what can we conclude?
W.
We can conclude W. This is tautologically implied by 1 and 4. And so now we're using premises 1 and 4. Okay, with W, we can conclude A. So we know W, and we know either A is true or W is false. We know W is true, so A has to be true. So A, this is tautologically implied by 2 and 5. And now we're using premises 1, 2, and 4. Let's rewrite this one. 7. I may distribute this, the not through there. Not D and A is the same thing as not D or not A. So this is not D or not A. that is tautologically equivalent to line 3. So that's just rewriting premise 3. Okay, and now if I know D, and I know D's false or A's false, I know D's false or A's false, and I know D's true. So A must be false. Putting these two together. So line 8, putting together 4 and 7, we know not A. That was tautologically implied by 4 and 7. What were the premises we used on 4? Just itself. And what were the premises we used on 7? Just 3. So that's using premises 3 and 4. So now, putting together this line, I have A and not A. That's tautologically implied by lines 6 and 8. And now we're using premises 1, 2, 3, and 4. Contradiction. So now using rule, reductio ad absurdum, I can conclude not B. Not B using rule, reductio ad absurdum, starting on line 4 and ending on line 9. And for those of you who have done math proofs before, this is typically the line where we say assume by way of contradiction D, and then when we get to here, that's where we do the double arrows back and forth. And now this is only using premises 1, 2, and 3. We eliminated 4 as a premise for that conclusion. Anything weird? Okay.
Sure.
Uh,
How did you remove 4 as a premise? Like, explain to me again concept.
I had this, where this was line 4. Here's my P, here's my not S. And so here's my S. I showed that P and not S ultimately implies a contradiction. Here's my C. So P and not S implied a contradiction. Therefore, P implies S. P and not S implies a contradiction. There is the same thing as P implies S.
Interesting.
So I removed not S as a premise.
Okay.
And we're able to conclude S. I have 3 premises here that are consistent.
Right.
I say, what if S is false? Let's take that as a premise. And I find out, well, no, my premises are inconsistent. Well, then S must have been true.
I'm just having a hard time following that.
Well, do you follow it over here?
Maybe that's where I need to follow it.
Yeah, I'd start over here.
So P and not S implies C, a contradiction. Now, is that what? Oh, and C is just false, false, false. Oh,
Yeah.
I see.
Maybe it'd be easier to just put a false here. Imply something false. And forget this whole row.
Huh.
P and not S implies false. Implies something false. Like a contradiction. Something that's always false.
Is there a way to put that in like a sentence, maybe?
Put that in a sentence. I can do it with math proofs, because we use those all the time. We do assume by way of contradiction something, And we find out that's impossible, therefore it must be true. Trying to think of an intuitive, easy one. I think the first one that comes to mind is proving the square root of 2 is irrational. I don't know. I need to think of an example. My mind's blanking right now.
Yeah, I mean,
Trying to say in words, if P is true and S is false, gives us something impossible. Therefore, if P is true, S also has to be true. If P is true and S is false, is impossible. Therefore, if P is true, S has to be true.
okay. Alright, let's try to make a little bit of sense, because
Say it one more time without the if, because I said it counted. P being true and S being false is impossible.
yeah.
Therefore, if P is true, S has to be true.
Because otherwise it would be impossible.
Right, because S can't be false. We can't have P is true and S is false. That leads to something impossible. So if P is true, S has to be true.
Interesting.
So that's what we did over here. We said if P is true and S is true and S is false, that leads to something impossible. Therefore, S has to be true. It's kind of weird that S is not D. Don't get confused by that.
That's interesting. Okay.
Okay. So that's the end of that. Now it's just whatever homework problems you guys want to do. So we went through chapter 1 homework. Which was that. So starting in chapter 2, find the first exercises. Are those exercises? Yes. Okay. Huh, that's teeny. Alright, number 1. Construct specific counterexamples for the following 2 fallacious rules of inference. For A, give a different example than the one in the text. I don't know what's in the text, so I'll do that. The traditional names of these 2 fallacies are indicated. Fallacy of affirming the consequent. From Q and P, we infer Q. Oh, if you know Q and P implies Q, then we may derive P. That's false. And then the fallacy of denying the antecedent. So they had all their names for these things. From not P and P implies Q, we derive not Q. So these are both bad rules of logic. Let's make it quick to our intuition that these are bad rules of logic. So we know Q, and we know P implies Q. Those are 2 things we know. Maybe don't put an and there. We know this is true and that's true. Those are our 2 premises. And we try and conclude from that P is true. The way we can show that that is invalid is to come up with a scenario where Q is true, P implies Q is true, but P is false. Maybe write this out as an argument. So the argument they're trying to say is, if you know P implies Q, and 2, you know Q, then you can conclude P. We're saying that's invalid. The way we show it's invalid is we come up with an interpretation where these are true, but our conclusion is false. So what can a possible interpretation of that be? We could have P be any false statement, like 2 plus 2 is 5. Q can be any true statement. The sky is blue. and we're good. Is it true that if 2 plus 2 equals 5, the sky is blue?
Mhm.
Yes. Is it true that the sky is blue? Yes. Therefore, 2 plus 2 equals 5. No. Invalid reasoning. Let's try the next one. From not P, and P implies Q. So we have P implies Q, we got not P here, and we try and conclude not Q. Still works. Same thing. If 2 plus 2 equals 5, the sky is blue. Yes. 2 plus 2 is not equal to 5. Yes. Therefore, the sky is not blue. No. All right. Using criterion 1, that's the criterion that says we should only be able to conclude true conclusions from true premises. Using criterion 1, decide which of the following are valid rules of inference. For as well as which you think are invalid, construct a specific counterexample, just like I just did, to show it violates criterion 1. That is, give an example in which a false conclusion is derived from true premises by using the invalid rule. All right, so same thing I just did. Any of you want to do them? You want me to do them? You want to do them? Too easy, no point even doing them?
I'll do. So they're not invalid. It says choose which ones you think are invalid.
Some are valid, some are invalid.
Oh,
The
okay.
ones that you think are invalid, you have to show they're invalid.
I think this is valid. If we know that P and Q are true, then we know P and Q are true.
Yep, can't argue with that.
That's, okay, alright.
This one is invalid. My counterexample is P being true, and then Q being false, which makes these two true, and then we can drive Q. C is true. Remember that. Well, it's the same thing we've been using over and over again. If P or Q have to be true and Q isn't true, then P must be true. So we can drive P. And then this is definitely invalid. So P being false and then Q being true makes this and this true, and then makes that false.
Right, so for that one, you can use the exact P and Q we had.
Yeah.
So is it not the case that 2 plus 3 equals 5? Yep. Is it true that 2 plus 2 equals 5 or the sky is blue? Yep. So can we conclude the sky is not blue? Nope. Okay. Next one. Alright, suppose someone proposed as the only rule of inference from P we may derive Q or not Q. Does this rule violate criterion 1? Is it valid to conclude Q or not Q from P?
Sure. Oh, is it invalid to say that's the only rule of inference?
Well, so far we're just thinking about criterion 1. Does it violate criterion 1?
No, it doesn't.
No, it doesn't violate criterion 1. Because it's always the case that we have Q or not Q. That is a true conclusion.
Mm-hmm.
And so, saying P implies Q or not Q, from P we may derive Q or not Q, yeah, because we can use Q or not Q anytime we want. It's one of those weird tautologies that we can just use that's not logically implied or logically equivalent to something else. It's just a tautology in and of itself. Okay, so does it violate criterion 1? No. Does it violate criterion 2?
I can't remember.
Criterion 2 says, our rules of logic better enable us to come to every valid conclusion that logically follows from our premises.
It does violate it.
And yes, if we had that as our only rule of logic, it would violate criterion 2. We could prove hardly anything if the only thing we could use is P implies Q or not Q. If we couldn't use any of these other rules we have written out here. So yeah, that would violate criterion 2. 4. Construct a non-valid rule of inference, which by itself will satisfy criterion 2, but violates criterion 1. Alright, let's think. How can we do that? How can we come up with a rule that is good for criterion 2, but invalid for criterion 1? We can prove everything that logically follows, but we can't prove just those things that logically follow.
You could do Q and not Q implies P. Because then P could be anything. I don't know, like using the vacuously true.
Yeah, I think that's the way that we have to do it. We have to introduce vacuously true. So, if we accept as a rule of logic proving from a contradiction, then yeah, we can derive everything. That's why I say if you allow one falsity into mathematics, I can suddenly prove anything, because I can prove it vacuously. I might have a direct way to prove it as well, but I can for sure prove it anyway, because I just do false implies that thing. It's always true. This is what you're getting is false. Make sense? So we don't have a rule of logic that from a contradiction we can conclude any new premise. Which one was that? That was 4. Oh, we didn't really need to scroll. 5. Utilizing the discussion of sentential interpretation, explain exactly why the following rule of inference violates criterion 1. From Thomas Jefferson was president, we may infer Jane Austen wrote Emma. I'm not sure what he's after there. Note that this is not a case of a true premise and a false conclusion, since both statements are true. There's just no rule of logic that connects them.
But true does imply true.
Well, those both happen to be true.
Yeah, I'm just saying.
But in this case, we're saying from A, we can conclude B. We could also pick A was a sentence. We can replace whatever that sentence was with 2 plus 2 equals 4. And B could have just as easily been a sentence, 2 plus 2 equals 5.
Oh, I thought it was saying that exact scenario violates criterion 1.
No, I'm saying the rule of logic being used in that argument. And the rule of logic he's using is from one sentence that happens to be true, we conclude another sentence that happens to be true. But that doesn't make it a valid rule of logic, because it's only a valid rule of logic if it's true under every interpretation. Alright, which of the following sentences are sentential interpretations of the sentence, it is raining or it is snowing? Okay, so we want sentential interpretations of it is raining or it is snowing, which means we have to preserve the overall structure of R or S for raining and snowing. We can add substructure, but the overall structure better still be a disjunction. Otherwise, it's not a sentential interpretation. Make sense? All right. If it's raining, then it's snowing. Is that a sentential interpretation? It's a sneaky one. It is. Because remember, if then is the same thing as not R or S. We still have a disjunction. We just put a negation in there. So we just added substructure. It's still overall a disjunction. That's a sneaky one. That's a tricky author. All right, it is snowing. Is that one?
No.
No. We completely lost a bunch of our structure. That's no longer even a disjunction. It is snowing or it is snowing.
I think he was.
We just replaced R with S. So now we just have S or S. Isn't that valid?
But you lose the fact that there's two different variables.
Right, it violated one of our rules of sentential interpretation. You have to replace in all instances, and you can't just plug back in. Because now this is just the same thing as S, is another way to see that,
Right.
which is loss of structure. So no, you just barely substituted in the same thing for two different things. You can't do that. Because you potentially lose structure. It is snowing or it is raining. Is that different?
No.
Oh, it just changed the order. Okay, that's a sentential interpretation. We interpreted R as S and S as R. We gave each of them their own distinct sentences. So still valid. Either it is snowing and it is raining, or it is not raining.
Yeah.
That one works. So we said either it is snowing and it is raining, or it is not raining. So we kept our overall structure, still a disjunction. We replace the S with not R, and we replace the R with S and R. Okay. Which of the following assertions is true? If it's false, give a counterexample. Okay. A sentential interpretation of a sentence P must have the same number of distinct atomic sentences as P. So if our P is, get some white space right in, something like R and T, when we write it as atomic sentences, so it's that atomic sentence and that atomic sentence, what he's saying is it true that every sentential interpretation of this would have to have exactly two atomic sentences?
No.
And the answer is no. We could just as easily replace that T with R and P or Q or R, or not R, that's the only one we have to avoid, or S.
We can do R. I think we did it in the
Can we do R?
in the problem above. We did it.
I don't know what you think about that. Maybe
Either
we
it's
can do R.
snowing and it is raining.
I don't see why we can't do R. Still true or false? True or false? I think we're okay with R. So now I'm not positive.
All I know is we did it in E in the problem above.
Yeah, so now I'm wondering if we messed that up. It seems like if you allow R to be entered in there again, you can break it. Because then I can get, no, it would still work as an interpretation. Yeah, I don't see why not. So, yeah, I think we're right. A is false. A sentential interpretation of a sentence P must have the same number of distinct atomic sentences? Absolutely not. A sentential interpretation of a non-atomic sentence P must have the same major sentential connectives as P. We still have to preserve the overall structure, and that one's true. A sentential interpretation of a sentence P must have the same number of occurrences of sentential connectives as P. A sentential interpretation of a sentence P must have the same number of occurrences of sentential connectives as P. Now, we can increase how much a sentential connective occurs. Like we had before. We started with a R and T, and we replaced that with a R and P1 or P2 or P3. Notice that here, or showed up 0 times, here, or showed up twice. So we had a different number of sentential connectives. Alright, a sentential interpretation of a sentence P must have at least as many occurrences of, not necessarily distinct, atomic sentences as P. And that one's true. We can't end up with less atomic sentences when we do the interpretation. We could have only ended up with more. Like if my initial sentence I'm doing a sentential interpretation of is R and P or Q, when I do a sentential interpretation of this, I'm still going to have at least 3 atomic sentences.
I'm getting caught by the not necessarily distinct ones. Is that saying I can just do R for every one of those spaces there?
P must have at least as many occurrences of not necessarily distinct. That's a good question. Yeah, that just struck me. Let's go back and read exactly what sentential interpretation is. Is it in here? Criterion 1, criterion 2. Logically follows if every sentential interpretation, so there's where we're using it, but where do we first define it? I wonder if this will work. Probably not likely. Oh, maybe. Come on, boy. A sentence P is a sentential interpretation of a sentence Q if and only if P can be obtained from Q by replacing the component atomic sentences of Q by other, not necessarily distinct sentences. Okay.
Oh.
So they don't have to be distinct, so we screwed up that other one. So it is raining or it is raining was a sentential interpretation of it is raining or it is snowing.
Even though you're losing structure?
We can simplify to lose a structure, but if we don't simplify to lose a structure, then we still have the structure there.
But if you took a sentential interpretation of that thing that you just...
Because, yeah, when we say it's a tautology, we say under every sentential interpretation it has to be true. So when we replace it with the same ones, or when we replace it with different ones. So that actually doesn't bother me now that I think about it. So we screwed up that first problem. It is raining or it is raining is a sentential interpretation of it is raining or it is snowing.
Right.
Which makes sense. If it's a tautology, replacing your variables with the same value doesn't matter, it's still a tautology. Which is ultimately what we use sentential interpretations to capture, is the notion of a tautology.
Right.
So that doesn't bother me. Glad we looked that up.
Where can I get this book? It's PDF.
Email me and I'll email you.
I think I did.
Or, I mean, text me and I'll email you. I sent you the discrete math book. Oh, yeah. Makes sense I put it there.
Well, okay. let me see.
So it's also on the Facebook page. Oops. What round are we on? We just did that. I can't have posted that much on that page, so.
Are we doing all the problems from chapter 2?
Oh, here it is.
Where are the next problems? Right at the end? I don't know. We can keep going as much as you guys want. You guys want to quit there, or do you want to move on to the next set of exercises?
I was got I got a bunch of stuff I got to do before bed.
All right, then we'll call it there.
And you guys can keep coming.